Welcome to part 2 of the sequences and series topic. In this video we'll be looking at arithmetic sequences. Before we get into what they are exactly, I want to show you 3 patterns. So the first one here, let's look at what's happening as we go from one term to the next in the sequence. We can see that the pattern is we are adding 4. What about the second sequence that we have over here? Well, in this one we have a difference of 2, but then the difference is 6 between 3 and 9, and then the difference is even bigger again. So it's not an addition, but rather a multiplication for this pattern. So we're tripling, or timesing by 3 each time we move from one term to the next. And then the third sequence, what's happening here? Well, we can see we're decreasing, but it's by a constant amount. So we're subtracting a half each time we move from one term to the next. So out of these 3 sequences, the ones where I've used green, these are what we would call arithmetic sequences, because they have a common difference between the terms. In this case, the difference is 4, and in this case, the difference is minus a half. This sequence over here, where I use red, is a different type. The difference, if we look at the difference between the terms, that changes, like we talked about before. So this is a different type of sequence that we will look at in a future lessons. But for now, we are going to be focusing on these type of sequences. So let's formalize what we've talked about here. In an arithmetic sequence, each term is a constant amount more than the previous term. And this constant is called the common difference, D. So we use the letter D to represent this common difference or constant amount that is between each term. So if we were to go back to those first few sequences that we were looking at, the 2 arithmetic sequences here on the left, we would say that D, the common difference, is 4 for this first sequence, and that it is negative 1/2 for this third sequence. And it doesn't apply to this because it's not an arithmetic sequence. More generally though, how do we calculate D? Well, since it's constant and is always the same between any 2 successive terms, if we go to any general term, so the nth term, and then we look at the term before that, so t of n minus 1, and we find the difference between the 2. This gives us our common difference, D. Now if we play around with this equation a little bit, we can make Tn the subject. So Tn would be equal to, and if we add this t of n minus 1 to the other side, we get t of n minus 1 plus d. And that makes sense, right? So any nth term is the prior term plus the common difference. But what's neat about this is what's called a recurrence relation. So a recurrence relation is an equation that defines a term by referring to the previous term. And this is what the recurrence relation looks like for an arithmetic sequence. So let's do some examples now. Example 1. If 5x 31 is an arithmetic sequence, find the value of x. So it's arithmetic, which means that there is a common difference between the first and second term and between the second and third term. Now formally we could write this as term 2 minus term 1, so that's looking at the first difference. Because it's constant, that has to be equal to the next difference between term 3 and term 2. So substituting in the specific values and pronumerals that we see, term 2 is x, term 1 is 5, so x minus 5 has to be the same as 31 minus x. And now we have a simple equation to solve. So let's add x to both sides and get 2x, and we'll add 5 to both sides, make this 36, and then dividing both sides by 2, we see that x must be 18. And just as an aside, what does that make the common difference? Well, if we're going from 5 to 18 to 31, or if we look back at these lines, we can see the common difference would be 13. But that's just an aside. Our answer to the question is here with x equals 18. Alright, second example. K plus 2, 3k plus 2, and 6k minus 1 is an arithmetic sequence. The first part, we have to evaluate k. So, same kind of setup as last time. Because it's arithmetic, there's a common difference from one term to the next. In other words, for this particular one, we could say term 3 take away term 2 will be the same as term 2 take away term 1. And then let's substitute what we know. So term 3, that's 6k minus 1. And we want to take away term 2, which is 3k plus 2. Notice the use of brackets here, just to avoid any potential mistakes. And then term 2 take away term 1, well, that's 3k plus 2 minus k plus 2. Okay, let's collect like terms and simplify both sides. So we have 6k take away 3k, that's 3k, and then we have negative 1 minus 2, so that's negative 3. On the right hand side we have 3k minus k, which gives us 2k, and then we have 2 minus 2. Sweet. Let's subtract 2k from both sides, and we get k, and at the same time we will add this negative 3 to find that k is equal to 3. Now on to part B. We need to find the common difference. And so it would help here if we actually knew the value of term 1, term 2, and term 3. And we can work that out now because we know that k is equal to 3. So term 1, 3 plus 2, that's 5. Term 2, 3k plus 2, 3 lots of 3 is 9, plus 2 is 11. And the third term, 6 lots of 3, which is 18, minus 1, that's 17. So now looking at this, we can see that the common difference is any term minus the term before it. So whether that's 11 take away 5, or whether that's 17 take away 11, in either case the common difference is 6 for this arithmetic sequence. Now we've already seen that the general term, Tn, can be expressed as a recurrence relation, where it is the term prior plus the common difference. But is there another way that we can express the general term Tn? So before we go any further, we're just going to introduce one more variable that commonly gets used, and that is the letter A for the first term. So the letter A is often used as the value of term 1. So if we start off with an arithmetic sequence, where term 1 equals A, then using this recurrence relation, what's term 2 going to be? So term 2. Well, term 2 is just the previous term, term 1, plus the common difference, D. But we have just said that specifically term 1 is now called A. So we have A plus D. What about term 3? Well, term 3 is term 2 plus the common difference, but term 2 can be expressed as this A plus D. So there's term 2 in the brackets plus the common difference D, and we can simplify this a little bit, can't we? We have A plus 2 lots of D. What about if we kept going? So I'll give ourselves a bit more room. What if we went on to a fourth term? So T4 is the third term, T3, plus D, the common difference. However, T3 is A plus 2D. We've just seen that here. Plus D again simplifies to give us A plus 3 lots of D. So do you notice a pattern? I mean, we can see that all of them have A involved, starting with term 1 that has A. All of them have a single A. But what about the relationship between this number here, the 3, and the term that we're up to? Back in term 3, this number and this number. And likewise here we have 1 lot of D. How does that relate to the 2? Well, in each of these cases we can see that the number attached to the D, is 1 less than the term number that we are up to. So that means we can generalize what we're seeing here to the following. Tn is equal to A, so there's always an A at the start, plus some number times the common difference. And that number is always 1 less than the term that we are at. So for the first term, it's 0. There's 0 lots of D. For the second term, it is 1 lot of D. For the third term, it is 2 lots of D, and so on. And so this way to express Tn is actually a very useful tool for us. So let's do some examples now where we'll see how this can be used. Example 1. Find the 20th term of the sequence 3, 10, 17, and so on. So we want to find the 20th term, T20. And we're going to use this equation to help us get there. But first of all, it's worth just noting down what some of our values are. So A, which is our first term, is equal to 3. D, the common difference, we can see is 7. And N, well, we're after the 20th term, so N is 20. Using each of these values, we can substitute them in to the equation. So we have 3 plus, now we'll do it properly, we'll go 20 minus 1, but of course you're more than welcome to say that that is 19, which we'll do in our next line, and we have D equal to 7. So 3 added on to 19 lots of 7. When we calculate this, we get 136. So this is quite an efficient way to figure out the 20th term. On to our second example now. Find a formula for the nth term of the sequence 2, 8, 14, and so on. So once again, we want to be using Tn equals A plus n minus 1 times d. And in this case, we're after the nth term, so we are going to keep n as n. The only things that we need to set up first of all are what our a value is, that's 2, and what our common difference is. And we can see that we are jumping up by 6 each time. So substituting those values in, we get 2 plus n minus 1 times 6. And so if we wanted to make this look a little bit nicer, we would expand the brackets here. So we have 6 lots of n minus 6, and then collecting like terms, the 2 and the minus 6 gives us negative 4. And so there's our formula for the nth term of this sequence, 6n minus 4. This third example is a little bit different. Find the first positive term of the sequence minus 50, minus 47, minus 44, and so on. So we can see all of these are negative, but the numbers are getting larger. So at some point we're going to reach 0 or cross over 0, and then we will have positive terms. But what's that first positive term going to be? Okay, so to set this up, we are saying we want the term that is positive or greater than 0. So we want a plus n minus 1 times d to be greater than 0. Now, a is equal to negative 50, and our common difference is 3. We're going up by 3 each time. So let's substitute those values in, and we get negative 50 plus n minus 1 multiplied by 3. This has to be greater than 0. Let's tidy up a little bit, and we'll see if we can solve this inequality. So we have negative 50 plus 3n minus 3. That simplifies to 3n minus 53 being greater than 0. If we move the 53 to the other side, we get 3n must be greater than 53, and when we divide both sides by 3, we get 53 over 3. Now this is where decimals will be helpful. So calculating 53 over 3, we get 17 and 2/3 or 0.66 and so on. Now n can only take on integer values, right? As we're counting through our terms, we have our first term and our second term and so on. So only counting numbers. In order for Tn to be greater than 0, we've got to the point where n must be greater than 17.66. So n equals 17, or the 17th term. The 17th term will still be less than 0. So the reason I'm making a point of this, even if this said 17.2, you might be tempted to round down, but if n must be greater than 17.2, for example, then it is the 18th term. Right, is the 18th term. That is the first positive term. So this is the first positive term. The 17th term would still be negative. even if we got an answer like this. But we're not done, because we were actually asked to find the first positive term, the actual term, not at when it occurs, not at what position, but what it actually is. So going back to our equation, we can substitute n equals 18 in now. So we know that a was minus 50 plus n minus 1. So n minus 1 is 18 take away 1, and that's times by the common difference of 3. And when we calculate this, we see that we get 1. So our first positive term is 1. Okay, final example. The fifth term of an arithmetic sequence is 37, and the eighth term is 55. We need to find the common difference, d, and the first term, a. So this one's a bit tricky. We've got two things to find, but we do have two pieces of information. So that looks good. So what do we know? Well, let's start with our first bit of information, the fifth term. So that's T5. Using our formula of a plus n minus 1 times d, we don't know a yet, but we do know n. In this case is 5. And we don't know d. We know that this fifth term, however, is actually equal to 37. So we can say that a plus 4, 5 minus 1 is 4, a plus 4 lots of d is equal to 37. That's one equation. Likewise, with the second bit of information, the eighth term is equal to 55. So we can set up a second equation that says a plus 7d is equal to 55. With two equations and two unknowns, we can now solve simultaneously. Now you may wish to make a the subject in one of your equations and substitute that in to your second equation, but I would recommend the elimination method for this. So simply equation 2 minus equation 1. When we do that, the a's will cancel, a take away a disappears. Then we have 7 lots of d take away 4 lots of d, which is 3d, now equals, and then we have 55 take away 37, and that gives us 18. We can therefore see that d is equal to 6 when we divide by 3. And now we just need to work out a, so we can go back to either equation 1 or equation 2. I'm going to go with equation 1, so we'll sub d equals 6 into equation 1, and we get a plus 4 lots of 6 is equal to 37, and solving for a, we have 37 take away 24, which gives us 13. So we've figured out that the common difference is 6 and the first term, a, is 13. And that's our final example. Great job.